All right, so let's start with the discussion that we had last lecture on Monday. We talk about the steady state response of base motion, which we had the similar topic except without damping. So we have the base motion and the main motion, which is x. And they are all absolute motion. We compare this motion, x and y, with the absolute observer. So y is moving ups and down, but a harmonic motion. Like, for example, 10 millimeters sine 100 t. So we drew the free body diagrams and we wrote the equations. Turn out that we have sine and cosine, but no problem. We can solve them individually, each differential equation, and then superposition concept. And for us, always the standard equation is, I'm going to write it again, it's always at this corner is the mx double dot plus cx dot plus kx equal to f0, sine or cosine doesn't matter, omega t. That's the standard equation. All right, so this is what we are hoping to get at the end when we solve a problem. And then we will use the same equation to solve it. Now it is the form of f0 that changed. For example, in this problem, our f0 is ky, and another time it is cwy. So we solve them separately as if we have two differential equations, and then we add them up. So a lot of math, but we skip those math. It's not important for like this course or even in future. But if you are interested, it is in your textbook, and you can also solve it for yourself as a practice. Or you can go with xt, xei, omega t as a solution, substitute it there, do all the math, and then at the end, you will get to xt, x sine omega t plus phi. That's the final answer. So in this final answer, we called x here the magnitude or the amplitude of vibration, and phi the phase of vibration. So which we talk about that phase, we said there is a delay. This angle shows that there is a delay between base and mass. Now when I move my base ups and down, m is moving with that, but with a delay, right? If I don't have damping, these two are going to move ups and down together. Later, I will show you a similar simulation that you saw 2 lectures ago with atoms with this one. And so you will see when we have damping, there is a delay between these two. And that delay can be calculated by phi, and always it has this negative sign. So we attempt to plot or simplify everything. So this is our answer. X is y, and like capital letter Y, which is the magnitude of base vibration, multiplied by a number. That number, we call that number m. And again, at the end of, because at the end of last lecture, I had some question, this m is different for different problems. For example, when we had a rotating system, this m had a different form. When we have damping, it has different form. For base motion, it has a different form. Like, for example, if I go one slide back over here, okay, so m has this form for a question which is not a base motion. One slide back.
Will we ever have to divide? Oh, sorry, I'm just hearing the echo in the room.
That's okay, go ahead.
Will we ever have to derive the formula for m, or will this be set cases for each one?
No, you don't have to drive it. We will set cases for each of these one. For example, for a case when you have f0, all right, so we will see m has this form. All right, m has this form, which we plot them, and we also have other details about it. Now, you don't have to drive them, so you will just use them. But remember, they are different. For example, for this case, m has this form. And now when we get to the base motion, m has a different form. When we talk about force, how much force goes to the base, which is next topic, you will see M has a different form. Depends on the scenario, M has a different form, but there are like 3 scenarios, and you will see, we will summarize them, 3 different M's for each of these scenarios. All right, so for this one, we attempt to plot the graphs. Of course, we start always with the easy case when zeta is equal to 0, which is the previous scenario that we had. My graph starts from 0, goes to infinity at 1, and then comes back. There is this key number, a square root of 2, which we discussed it before. It results in M equal to 1. M equal to 1 means that the magnitude of vibration for X is equal to the magnitude of vibration in base. Whatever I have in base, the same things goes to M. And why this is critical? Because again, we discussed it, we wish that there is less vibration going to the main system mass, M, right? Maybe the main system mass is a sensitive system, we put it somewhere, and we want less vibration to go there. Maybe this mass M is you sitting in your car, and the base is the road vibration. So you like to design this K and C in a way that less vibration transfer to you. So that's why we wish to be around omega over omega n after a square root of 2. All right. So, and then for scenarios when we have zeta, so we have this graph which we can also plot it. And I ask you to take the derivative and figure out where the maximum happens. Anybody tried to take the derivatives of this one and see where the maximum happens? Remember, we have an M, which is a function. For simplicity, this function, I replace omega over omega n by like a new variable R. And we wish to find out that where this maximum M happens. So we take the derivative, set it to 0. We did it for the previous scenario, right? Over here. Again, to refresh your memory, we have a function M. We replace that omega over omega n with R. We take the derivative, we set it to 0, and we found that R equal to this number, which has nothing to do with omega d. I emphasized again here, omega d is this function and has no business in our discussion here. Okay. So this is where the maximum happens at this omega, which is slightly below 1. So that's why still we consider omega equal to omega n as the resonance. But later you will see, I will discuss, even we try to avoid a bandwidth closer to omega equal to omega n. But that's future topic because we don't want to get to the peak. Okay? So the same things here, if you take the derivative, we will find out somewhere maximum happens. Anybody did that? You can tell me what was the result. If not, please do it later. I'm not going to do the derivatives. So if we draw the like graphs for other zetas, so let's say this is zeta equal to, for example, 0.4. I just, some arbitrary number smaller than 1, but bigger than 0. So 2 things that it's important to know. First is that this function, the pink one, when I have a zeta, whatever number, still is crossing at the square root of 2. All right, so you can test it with this function. Put a square root of 2 here in this function. You will see this value becomes 1. So numerator and denominator becomes the same, and you would get M equal to 1. So no matter what is zeta, if it is 0, it is 0.4, still at a square root of 2, the value is 1. But here is an important thing to pay attention. And that is, okay, let me try one more graph, and then you can tell me what's going on here. And I try to do that one with a different color so you can see it. Maybe a better color. Okay, this one. So that's the green one. And the green one, let's say zeta is equal to 0.2. The red one, zeta is equal to 0. And the pink one is zeta equal to 0.4. Later with the computer, you can plot them. There is a code that I put at the end of this chapter that you can plot this more accurately and change this zeta and see the values. But for now, just for the sake of discussion, what you can notice from this graph, anything that pick your attention. So beside that, the fact that the square root of 2 is when m is equal to 1, and we wish to be after a square root of 2. Anything else? You can unmute yourself, tell me, or just type in a chat. Okay, I will give you a hint. Take a look at the graphs before a square root of 2 and after a square root of 2. And see if you change zeta, are they decreasing or increasing? Okay.
So before square root 2, you can see the peak is decreasing as you increase zeta. After square root 2, it's the opposite.
Exactly. Thanks, Apple. So as Apple mentioned, the difference is before a square root of 2, when you have, let's say, more damping, it's a good thing. If you add damping, you see m is becoming less and less. All right. So like the worst case is 0. When zeta is equal to 0, that's the worst case. But after a square root of 2, maybe damping is doing some damage for us, right? So you will see the more damping you have, it's gonna increase m, but still you are less than, of course, 1, right? So for example, let me try another one, maybe this time with a different color. Oops, no. It's difficult to plot it like that. It had, right? So this one, for example, let's say it is zeta equal to 0.8. So as you can see, the more damping, now it's not a good thing. If you are after a square root of 2, that's something that you need to pay attention. All right, so I'm gonna stop here. Let's give you some time to, if you take notes or think about what just happened, and if you have any question before we move to the next things. And I'm gonna stop here and check the chat to see if there is any question. Exactly, so Kieran mentioned the same things in the chat. Before square root of 2 and after square root of 2, zeta has different effect. On the left side, the more damping you have, the better. On the right side, the yes. So you draw higher m, high m. Yes, after the square root of 2, as you can see, right over here, maybe I'll show it like that. More zeta means m is increasing. Over here, more zeta means m is decreasing. Okay, I guess I Okay, I need to correct, you're right. I need to correct this brown one. Just, let me redraw it. You guys are right. Some of you are killing yourself to tell me that I made a mistake. And that's correct. Yes, that's the brown one. Thank you. So the brown one, right? Let's do it again. Should be like that. Please correct it, all right? So before a square root of 2, so the brown one is zeta equal to 0.8, right? Okay. Now it makes sense. Now let me check chat and see. Below the pink line, thanks, Nico. Yeah, you guys are right, yes. So here is the plot then, and we have M. Now we want to do one more things with this concept of base motion. Another thing that in vibration comes a lot is we wish to know how much force goes to the base. Because in design of especially cars, we need to know how much force goes to the chassis. We calculate how much vibration goes to the passenger, M, or to the main car, but now we need to know how much force goes to the base. Right, so that's the plan. Let me take that photo, like take that image, take it to the next slide, rather than me drawing it again. Copy that one, go to the next slide. And you guys have to, I guess, draw that things if you're taking notes. Oops, too big. Better. All right, here is our plan. We want to know if I have a base motion y equal to y sine omega t or cosine omega t, how much force goes to the base? F equation is something that we want to find out. Or some people show it by Ft, and just to indicate that this is the transferred force. So we'd better stick with Ft with the same things that people use. All right, so what we did, we managed to find the equation of motion. I'm just going to write them again here. The equation of motion, which was, I'm going to go one step there and copy what we had over here. Minus k x minus y minus c x dot minus y dot equal to m x double dot. I just wrote the equation that we developed in this slide before doing any simplification or any other things on it. Right? Where it comes from, of course, from free body diagram. And we know that on this base, right, the same force that we have here goes to the base as well. So like this one is C x dot minus y dot, and this one is K x minus y. So then I can claim the total force going to the base Ft is equal to K x minus y plus C x dot minus y dot. Can I claim that? So this is my base. To the base, I have a force Kx minus y, and I have a force Cx dot minus y dot. So the total force then will be sum of these two forces. But we already found that this value is equal to minus m x double dot here in this equation. So what is x? X, we found that it's equal to x e to power of I omega t. All right. Or we can just write its, let's say its form, x sine omega t plus phi, because usually with imaginary numbers, we are not that comfortable. So this is what we found for x. Now, if I take the derivative twice, x dot will be x omega cosine omega t plus phi, and x double dot gives me minus x omega squared sine omega t plus phi. All right, so far good. We have the equation of motion, the one that I just highlighted. We know the total force going to the base is the force coming from the spring and the force coming from the damping. This value, according to what we had before, is mx double dot. We managed to find x, which has this form. We take the derivatives. Now we substitute it there. So ft then will be mx omega squared sine omega t plus phi. All right, so this is the force that going to the base of this system. And this force, of course, is not constant. It's a function of time. It's harmonic, and it has a delay phi. But for us, when we do the design, is the maximum that matters. And that maximum is when this sine omega t is 1, or we just care about the magnitude. So the magnitude of ft is mx omega squared. So we managed to find x. I'm going to write it down again here. So from here, I can write down ft is equal to m omega squared, and x was, I'm going to move back one slide and show you what was x. X, we find x is equal y to these big square things. So it is y multiplied by this big guy. 1 plus 2 zeta omega omega n squared, 1 minus omega omega n squared, 2 zeta omega omega n squared. All right, so this is x that we had it in a previous slide. Now let's manipulate this equation a little bit. We like to make it nicer, something that we can plot it. So what I will do, let's divide everything by k and multiply by k. So I will write down k m omega squared divided by k. And then the whole thing's here, which I don't like to write. So what do I have here? M over k, right, gives me 1 over omega n squared, right? So from here, then I can make the conclusion that ft divided by ky is equal to omega n squared one plus 2 zeta omega n squared 1 minus omega n squared 2 zeta omega n squared. So let's stop here and make sure that the math is correct. So one more time, ft is this mx omega squared that we care, mx omega squared. We substitute x by this value that we found before inside this red circle. And then I divide everything by k, multiply by k. And we know m over k is 1 over omega n squared. It seems to be correct. Now, the way that we interpret the whole things here, we say this is the transferred force. The transferred force. All right. Ky or to the base. This is what we call it the static force. Like if I have, let's say, only y statically, if I compress the whole things, I would get a force of ky. And damping doesn't give me any force in a static. Remember, damping apply force when we have a speed. In a car sitting somewhere, no vibration, the only force is coming from the spring, from deflection of the spring. Damping doesn't do anything until it has some speed, some moves ups and down. So that's your static force, only ky, and ft is the force that transfer to your base. And the whole things now, we call it the magnification factors. See, now it has a different form. Your m now has a different form. Let's plot it and see how it looks like. So on x, I will have omega over omega n. And over here, I have these new m. So some key numbers for me is like maybe 1. And over here, maybe 1 also. We just put it there in case. So 1. And this is 1. Right? Let's try to plot these things and see how it looks like. We start with this simpler case when zeta is equal to 0. So zeta is equal to 0. When I have zeta equal to 0, so nothing over there. At omega equal to 0, we don't have any force. So this one is 0. And at omega equal to omega n, it goes to infinity. And then it will come back to 1. Right? Because at 0, your m looks like this. Omega over omega n squared, 1 minus omega n squared, right? And we care about the positive value, absolute value. Although in math, like this graph, this second part should start from minus infinity, but we just care about the magnitude. So we had this graph before. You've seen this one exactly for case when there was no damping. And you can see this formula is also showing the same result when we put zeta equal to 0. And as you can see now, the shape of this graph is different. At infinity, they go to like 1, right? So as I said, you will get different m for different scenarios, but you don't need to drive them. There are some standard one. And at the end, you will know. I guess there is one another one left, which we will discuss it today. So for the rest of them, the graph looks like this and that and so on, which with the computer you can of course do a better job, which the code is for you at the end, or even your textbook, it just shows the accurate graphs. Here I'm just showing it schematically, so you will see how they looks. All right, so this one is, for example, zeta equal to 0.8. I just made up these numbers, so you need to plot them with graph. This is, for example, zeta equal to 0.3. All right, so again, as you can see, at 1 or close to 1, we have the peak. As omega over omega n increase, like at higher speeds, you have less and less force going to your base. All right, and this is how we can calculate m. Remember, in your exam or in future, when you need to calculate ft, right? This is our target. We wish to find ft, the force, because that can gives us some information to calculate the stresses and other things. When we design things, how strong our base should be. So this ft divided by ky, let's say we have the stiffness, we have y, so we have ky. All I need is this m. So to calculate m, I need to know what is the damping, what is the speed, omega, what is the natural frequency, and we know how to calculate them. All right. So I'm going to stop here and see if you guys have any question, or if you want to take notes, spend some time, think about these things, and then we will go to the next topic.
Ahmad, quick question.
Yes, please go ahead, Alberto.
Since the part that we're dividing into is the static force, Ky, if we have a system where the equivalent, like the K of the system is something complicated, something different, would we just use the K of the spring, or would we use the equivalent K?
We use always the equivalent K. That's a good question. You always simplify your questions to get to, like to this equation, mx double dot plus cx dot plus kx equal to f0 sine omega t. And then when you have like a complicated system, this k may have a different form. This c also may have a different form, and m as well.
Makes sense. Thank you.
Okay. So let's take a look at this graph again and see we did everything correctly or no. Just trying to think about what I've plotted here. Square root of 2. I'm just thinking at the square root of 2, what will happen in this graph? Square root of 2 gives me this one equal to 1, it gives me 2. Okay, this graph, let's make it nicer. Sorry, guys, it's going to be the same, but it's not going to go to 1. It's going to go to 2. So let's try one more time. I'm going to see what will happen at the square root of 2. Square root of 2, this one has to be equal to 2. Am I right? Yes. Okay. let's do it again. Let's pretend that this is a square root of 2. In fact, it's not a bad thing that this mistake happened, because now you're going to remember that. Okay, so the square root of 2, when we put it for the case with zeta equal to 0, gives us 2. You guys agree? Or I'm making a mistake here? The square root of 2, m gives me 2. That's correct. So this graph then should look like go from infinity. And now it goes to 1. So that's the correct graph. So this is square root of 2 also is a key numbers. So that's when we rely too much on computer to plot things for us. Like in the past, when they didn't have the computer, wondering how they plot all these things. Now for cases when we have a zeta, still a square root of 2 is a key number for us. So it goes there and it comes back square root of 2. So that's that one. One more attempt. Yes. And another one with green. Okay, so let's assume that this is zeta equal to 0.8, and the pink one is the pink is zeta equal to 0.3, for example. But again, as I said, you can check the computer code, MATLAB code, and you can plot them. Right? Now it's better, right? So 2, at a square root of 2, always we get a magnification factor of 2. And you can check it from this equation. So it means, unlike the previous scenario, which at the square root of 2, your magnification factor was m, here at the square root of 2, your magnification factor is 2. It means at the square root of 2, m is 2, twice of the static force goes to the base. If you pass that point, you're going to get less numbers than 2. All right. Now I'm going to give you time to replot these things if you are taking notes and think about what just happened. All right. And again, for more accurate graphs, please check your textbook. And I'm just drawing the schematic of them. They are correct, like this one is correct, but just to see the exact shape.
So it seems like we'll always get m between 1 and 2.
For cases after a square root. That's correct. Yes. I guess when you have a very, very large zeta, like not quite sure, you have to check the plot. I guess even after that, you get your graph going like that. But you need to check that one, make sure.
So is that zeta greater than 1?
Greater than 1, which is not the case that we are interested, because for those cases, there is no vibration. All right, so I hope it's clear. So far, we have the magnification factor for the force. Again, I'm emphasize here, this is for force. and your formula is always the same. So this M, you don't need to derive it, it's the force. What changes is this omega n and this zeta, because they depend on K and M, as Alberto asked, the equation, when you have, let's say, a different system, you need to find out what is the M, what is C, what is K, and based on those numbers, you can find omega n, which is K over M. For a rotating system, for example, M might be ml squared, K might be b theta, b K, and C might be different numbers. And C and zeta, you know how to calculate it. It is C over 2 square root of Km. All right. So let's now talk about accelerometer. Accelerometer, like the concept of, they are made based on the concept of base vibration. And this is like a schematic of an accelerometer. Probably if you Google for an accelerometer, let's just do that, we will just see a small shape of sensor. Images. Not Arduino, even you can find one for Arduino, but most of accelerometers, they looks like just a cylinder like this one. Or like this one. And your cell phone also has one. So, but inside, this is what actually an accelerometer has. There is this spring, which is being pre-compressed because we don't want it to be loose. A little mass, this mass is very, very small, depends on the accelerometer sensitivity. And people use a material, a piezoelectric material, and you know piezoelectric material has this property. If you compress them or if you bend them, they produce a little bit of electricity. So we will get that electricity, and based on the voltage or current that we get, we can then estimate what is the vibration. So why it is in a category of base motion? Because let's say you put an accelerometer on a ground somewhere or on a machine, and that machine is vibrating. Let's say this is the vibration of the ground, yt, and it can be any function. That's the vibration. So the vibration goes to this system, M is vibrating, and it gives you a magnitude of vibration, which the result will be an output. So we can model this system then as, let's say, a spring, a mass, M, and then for the piezoelectric, let me use a different color for the piezoelectric. It is a spring and damping. So let's say this is K, and now this is a K of piezoelectric and C of piezoelectric. And this is our base vibration, YT. All right. So this YT and this is K. So you can now find how much M is vibrating, X. So you can find actually XT. If you know YT, then you can find XT. But when you use a sensor, actually YT is the question. What is YT, right? Instead of YT, we will get some electricity here. So this is our output. But most of accelerometers, or all of the accelerometers, when you purchase them, they will tell you, for example, for every millivolt, this is the amplitude of the actual vibration. So there is like a graph or some data which tells you how to convert voltage to actual acceleration. The second thing that you need to know, this YT obviously is not a harmonic, not harmonic. Unless it is, let's say, a motor vibrating with just one rotation. It's a, let's say, a random graph. So then you may say, okay, how to deal with this random graph? And again, it is outside the discussion for this class. Just I'll tell you how it will be dealt. Right? The way that people do it is YT. After they do it, they get it, they do a FFT, fast Fourier transform. Like they say this random graph is made out of lots of frequencies, maybe a small frequency, harmonic frequency, a bigger one, and different amplitudes, of course. And so on, right? And that's the Fourier transform, omega 1, omega 2, omega 3, and a lot of omegas. So they do FFT, which is hopefully if you go to grad school, you will study it more. I will talk a little bit about it at the end of this course, how you can apply FFT, or in my other courses, I talk about FFT, but not here. Anyway, accelerometer, it used the concept of base motion. And I want you to do something as a practice, write the equation of motion. The equation of motion. But I want you this time to do this. This xt, consider this xt to be relative motion. So this xt, relative motion with the frame. My pen doesn't work. So relative motion to the base. Right? So assume that you are measuring the motion of M with respect to the frame X. Somebody is sitting inside this frame and is measuring this X. And assume that here you have a YT, which is like the absolute motion. This is YT. That is the absolute motion. All right. So you have this frame, this box. This box is moving with YT because it's attached to the ground. But this X is being measured with respect to like this frame. Like develop that one for me as a practice, and that is also important to work on it as well. All right, so with that, we are done for our today discussion, and one more topic left for the steady state response with damping cases, and that's the rotating system. You can also work on this one before the next lecture on Friday yourself. It is exactly similar to what we had before, except that case it was without damping. And this one will be done with the magnification factor and everything in this chapter. Thank you very much for listening. I'll see you on Friday again via Zoom and next week in person.